All right, welcome back.
Hey everybody.
We're going to do 6.1 today.
So vectors.
What's a vector?
It has magnitude and direction.
Yeah, I tried to steal the little thing from Despicable Me too, but they told me I was violating copyright rules, so
Yeah, well.
oh well.
Okay,
All right,
so
what is a vector?
directed line segment has magnitude,
And
direction.
quiet in the peanut gallery. All right, each vector has an initial point and a terminal point. So basically it's just a ray like in geometry, but
Yep.
it starts at some point and then it stops instead of continuing on like a ray does.
Okay,
So two vectors are what if they have the same magnitude and direction?
well if they're exactly the same, we're going to call them equivalent.
All right, and if we ask you to show their equivalent, what do you have to do?
We have to show their magnitude's the same and their direction's the same.
All right, easy enough.
Okay. So location, it doesn't matter where we put the vector, so we can move it around. So sometimes we're going to move it into what's called standard position, and that's going to have an initial point at 0, 0.
All right, so basically we just put the starting point at the origin.
Right.
That's easy enough.
Okay.
A vector that's in standard form can be written in component form. So really there's a lot of vocabulary here. Component form is going to have little, what do we call these? Vector brackets, if you will. They're little greater than, less than signs.
I didn't know, so I didn't say anything.
But it's going to be the endpoint of your vector where the initial point's at the origin, and we're going to call that component form.
Okay. So you'll know from those little brackets.
All right, the magnitude is just how long the vector is. So we're going to denote that with basically absolute value signs around a vector.
There's two different ways to write that. You can use a bold, that's nice, a bold V, or you can use a vector with a little half array on the top of it,
It's hard to write bold on your paper.
apparently.
So, all right. When the vector's in component form, the magnitude just is found by the distance formula. It's the hypotenuse of a right triangle. Okay? All we have to do basically is when we put AB, we're saying that we have a vector that starts at 0, 0 and goes to the point A comma B. And so basically what we're finding is the hypotenuse of that right triangle. So the magnitude is just going to be A squared plus B squared inside of our square root.
Sounds good.
All right? Easy enough?
Easy enough. Let's get to an
All
example.
right, the lower down the board we go, the worse this picture gets. All right, let P be 4, 1 and Q is at 10, 6. Sketch vector PQ and find its magnitude. Well, to sketch a vector, you basically just start at 4, 1 and draw 10, 6.
Okay.
So I already did that. It's over here somewhere. All I gotta do is find it.
There it is.
All right, so here's P, here's Q, and vector PQ basically goes from 4, 1 to 10, 6.
Notice there is an arrow at the end of that.
All right. Now we'd like to draw it in standard form or standard position. What is standard position?
Wait a minute, we have to find its magnitude first.
Oh, sorry, forgot that. All right, magnitude
So
is,
it's going to be our distance formula, right?
yes, so we're basically going to go 10 minus 4 squared plus 6 minus 1 squared, and it's all inside of a square root.
Magic buttons get us square root of 61.
All right. This marker's really fat. All right.
All right, standard position, we said it had to be at the origin. So that means we're
At the
going to
origin.
take point P, and we're going to move it over to the origin. Well, P is currently at 4, 1. So all we got to do is drag it left,
So we're at 4, 1. We're going to drag it left how far?
4,
1, 2, 3, 4,
and down 1.
down 1. So our new P is here and our new Q is here?
It is.
All right, now, so without counting on the graph paper, which we could do, basically this is a translation, right? We went left 4 and down 1, correct?
Correct.
So if we apply that to point Q, where is point Q going to be if I go left 4?
Well, left 4 from 10 is 6.
Down
Do that.
1?
5.
5? And then we're going to write it in component form, which means we're going to put little brackets around it like that.
Because it automatically starts at the origin when it's in standard form.
Piece of cake.
Alrighty. So algebraically, we need to show why these two vectors are equivalent, which
What-
means
We have to show the same magnitude and
direction.
direction. Okay, how do we do magnitude?
Well, magnitude was the square root of 6 squared plus 5 squared.
6 squared plus 5 squared was going to be?
Oh, look, 61.
61. That is
Yay,
the
they're the same.
magnitude of this vector, okay? That's the magnitude of vector PQ. How's that?
Beautiful. I like the
I don't know
scribble.
if beautiful is the right word to describe that. All right. How do we show the same direction when we're on graph paper?
Well, it kind of looks like a little ray, which is like part of a line. So how about let's count some slopes.
Slope. Okay, so originally to go from 4, 1 to 10, 6, we were over here, right?
Correct.
We went up 1, 2, 3, 4, 5, and we went over 1, 2, 3, 4, 5, 6. Yes?
Yes.
So the slope was up 5.
Over 6.
So PQ was up 5. I don't know which way over is, so I'm going to say
Sorry.
right 6. Is that all right with you?
That's great.
Okay, but the vector 6, 5 is obviously right 6 and up 5, is it
Yes,
not?
it is.
So This is also right 6, up 5, and it's in standard position. So are they going the same direction?
They are going exactly the same direction.
And since they have the same magnitude,
Then they are equivalent.
piece of cake.
Alrighty.
All right, so what if we don't have coordinates?
Well, if we don't have coordinates, we've got a better way actually to talk about our vector, because what we're going to do is a better way to talk about its direction using an angle measurement.
Okay, so we got an angle
Okay.
measurement.
We do.
Let's read the question this time. Consider the vector below with magnitude r in direction theta. If the endpoint is at xy, what is the component form of the vector in terms of r and theta?
Okay, well, if the endpoint's right here, then this is the point x comma y, correct?
Okay, so basically we just need to find what x and y are in terms of r and theta so we can write it in component form.
Okay. So, x, how are we going to find x? Well,
How
theta's
about we
right
use
here.
Cosine,
Okay.
because x is the adjacent side to our angle. So cosine of theta is x over r, which means x is equal to r cosine theta.
And since we will already be given r and theta, that helps
There
us
we
a
go.
lot.
All right, so how about sine of theta for the y value? So it's y over r, and then y would equal r sine of theta. Now, hopefully you realize that from the unit circle, on the unit circle, our cosine was x and our sine was y, but what was the radius of a unit circle?
1.
1, so this kind of still fits, doesn't it?
Absolutely still
Basically,
fits.
if we make the radius 2, then the x value is 2 cosine of theta, and so forth. So that is a very interesting little bracket
you.
we've got going on there.
I was just going to the component form.
There's the component form.
Alrighty.
But hopefully they can memorize that without realizing it's, not really that new.
No, you shouldn't have to develop that every single time.
No, we just write it.
Okay.
R cosine. Now let's see how easy this is. All right, go to the next problem.
Yes, sir.
Okay, so sketch a standard vector V, or sketch a vector V in standard position with magnitude 41 and direction 220 degrees.
Well, 220 degrees is going to be over there somewhere.
All right, and we're all pretty good at that. And if the magnitude is 41, how do we make sure that's represented on our picture?
We're gonna
Hey,
write
that was hard. We're done.
Ta-da! I like that problem.
All right, let's write it in component form then.
Oh, okay.
Maybe we should label the 220 in the previous problem so they know what the angle was.
Like
All right,
that?
so yes, so component form. If we know the magnitude and the angle, the component form is just going to be magnitude times cosine of the angle and magnitude times.
Sine of the
sine of
angle.
the
Can I name that vector v?
Sure, why
Just
not?
makes our notation a little better.
We named it V in example 3.
Okay.
So we got magnitude is 41, cosine of 220 degrees, comma.
Magnitude is 41 again, and then we need the sine of 220 degrees because that's going to be our y coordinate.
Is that all there is to it?
That's all there is to it.
Wow, that was easier than the other one.
How about you get the
keep
next
going.
problem? Oh, okay.
Oh. Oh, man. Oh, we're so close. Yay!
So what you just watched is Mrs. Cofield try to play the paper toss game for about the first time ever.
First time, I had to download it and everything.
It was rather entertaining, but basically what the paper toss game does is add vectors. The fan is blowing one direction, and you have to aim in the other direction, and most of you are going to do this just kind of because you're good at it.
Intuitively. It took me, I had a steep learning curve.
That's the word I was looking for. It's a big word. Okay, but basically what you did was add vectors together. You had to aim to the right when the wind was blowing to the left so that the thing curved in and went the direction you wanted to go.
And then I got it. Woohoo!
The direction you wanted it to go, that resultant vector is
Yes.
what we're going to call that, okay?
Okay.
So two basic operations we're going to talk about. First one's vector addition,
Adding, I like that.
all right? And we're going to talk about scalar multiplication, which is simply making the vector bigger or smaller in terms of like 2 of them or 3 of them or
Oh,
half
okay.
of them. We're just multiplying by a constant, okay?
I like that too.
When two vectors are added together, the answer is the resultant vector. Again, for the paper toss game, that resultant vector, we were
That's where the ball actually
throwing our
the paper
paper here,
toss
and the
section
trash
went.
can was here, and we wanted the resultant vector to go in the trash can.
Perfect.
All right, so we're going to figure out how to do this, okay? Okay, example 5. Let's actually try adding some vectors together.
Okay, sounds good. So we have two vectors, u and v, and u is 2, -3. Remember that standard form, so it's going to start at the origin, go to the right 2, and down 3.
All right,
Okay.
and v is in red down here, and it's at -5, -2, which means it went left 5 and down 2.
Correct.
We are being asked to double u, or double,
Double vector u.
double vector u, and add v.
Okay, so I need another blue vector, is that what you're telling me?
Yeah, we need 2 of them.
Okay.
And so we need them to go in the same direction, but we just need 2 of their magnitude. So I'm just going to make 2 of them here and fight with my board a little bit to try to get it to go the right
That's why
direction.
you're standing there.
But there we go.
Okay.
So now we've
it's
actually
2u.
gone how far to the right and
We've
how far
gone
down?
4 to the right now and 3 down, because we just doubled it.
6 down.
Thank you, 6 down. We just doubled it.
Fair enough.
'Kay.
Okay, so how do we add vector v to this vector?
Okay, well, I need to start vector v where vector u ended.
Oh, so can I just pick it up and move it? Because we
Yes.
said earlier it doesn't matter where it starts.
Correct.
So if I just start it there, is that adding 2u plus v?
It is, because we're going to go tip to tail, they call that.
Tip to tail. And so our final point is right here at, that is -1, 1, 2, 3, 4, 5, 6, 7, 8. Is that
Yep,
correct?
that is correct.
That's good to know.
So
And
there's our result
that is
vector.
2u plus v.
Yes,
so
it
if
is.
our trash can was at -1, -8, we would have made the shot.
We would have.
All right. Let's try the other example.
Okay?
How does one do subtracting vectors?
I don't like to subtract, so I add the opposite instead.
So basically this is vector u plus the opposite of vector v. Is that okay?
Correct. So now the question is, where's the opposite of vector v?
Well, a vector's got magnitude and direction, so the magnitude is going to be the same no matter what. It's just
Right.
the length of the vector. So the opposite must have to do with the direction.
So the direction is going to be the x and the y, correct? So don't we
Yes.
have to do the opposite of both of those?
So we just need to flip v around.
Yes.
So let's see if I can do this real quick here. Let's flip it one way and then we'll flip it the other way. And I think v then is going this direction now, or minus
Okay.
v. Is that okay?
That's great.
So here's minus v now. It's literally going in the opposite direction.
And again, if we're going to add those together, now we should be able to drag minus v down to the tail of the u.
So we just put it right here.
And now we have our resultant vector, which is
Which-
7 to the right and down
1,
1.
2, 3, 4, 5, 6, 7, and down 1. So that means our answer is 7, -1.
Yes, it is.
All right, well, this is all fine and good and fun, but they really can't drag vectors around on their graph paper, can they?
I guess they need a smartboard.
Yeah, well, that's one solution.
Figure it out. No, there's got to be another way to do this.
This is just a visual of what we're doing, but it's much easier to do this algebraically.
Okay?
So how do we actually do this?
We just do the arithmetic that we see right here. If I'm going to take 2u, we're just going to double vector u.
Right, because originally that meant we just went 2 to the right and 3 down, and then we went 2 to the right, 3 down again, which was 4 to the right and 6 down.
Yep. And to that, we're going to add the vector v, which is -5, -2, and that's literally sort of combining like
We're
terms,
just going
if
to
you
add
will.
the common components, if you
Yep,
will.
the
I just make something up.
Horizontal component and the vertical component. That really is a 1.
It's like somebody sitting on
Shush.
a chair.
Shush. Shush.
All right. So u minus v, again, we don't have to work as hard this time. We could do -v, or the opposite of v, and change the terms. So we have 2, 3 as a vector.
Thank you. 2 -3?
Yeah, sorry.
It's all right.
I'm not as helpful as I thought I was. Plus, the opposite of v would be +5, +2. And again, we just add the like components. So we end up with 7, -1.
Hey, that's what we got
just
last
like
time.
we did last time.
We're
All
smart.
right.
All
Nice
righty.
piece of cake. All right, so the next problem is basically the same idea, just with an application. If you're in
Okay.
physics or going to take physics, you might get to do some of this. The best thing you should do really is just kind of set these problems up. All right, you draw yourself a picture, figure out what's going on. We have a force with a magnitude of 2,000 Newton and 900 Newton acting on a machine part at angles 30 degrees and -45 degrees respectively. So draw these things semi-accurately and label everything
Thanks.
appropriately. That's a 30-degree, 2,000 Newton force.
Okay.
Yes?
It is.
All right, so what's
'Cause I
this
said so.
-45 degrees thing?
Well, we know where -45 degrees is.
Oh,
That's
it just
this
goes down
direction.
45, and it's going to be a little shorter than
It
the other
is.
one, but that's okay.
Doesn't look shorter to you?
That's all right. We'll label it.
How's that?
That's better. It's only 900 in terms of magnitude, and it's -45 degrees. So how do we add these resultant, or find the resultant force? If you're pulling at 2,000 newtons one direction and 900 newtons the other, where's the end result force going here?
Well, again, we could try to drag this over, but I'm not that good with the smartboard. But if I drag the red one to get the green one up here, same direction,
Okay,
then my resultant will be,
you're running out of colors.
I am,
We only got 4.
the blue one.
Okay, so, again, this is a little bit more difficult to draw on graph paper and to drag everything around. So can we just do this algebraically?
Right, and the arithmetic is the same thing. We're just adding the two vectors together. The difference is, what's the component form?
All right, so the component form, again, when we knew the angle and the magnitude, we could write 2,000, cosine of 30, comma, 2,000, sine of 30. That was the component of the first force.
Yep, that's the black one.
All right.
That's the degrees.
How about the second one? How about the 900, the red one?
Thank you.
Same idea, it's going to be 900, cosine of 45,
Cosine of negative 45.
Thank you very much.
Which won't matter for cosine, but it will for sine.
Yep.
Oh, look, trig's important.
You mean all that stuff we did the last few months actually has some sort of use to it?
Yeah, you can't forget that. I think
Weird.
I put my parentheses in the wrong spot, but you get the idea.
Okay, so how do we do this? Well, if we're going to try to do this by hand and to finish this up, we could go ahead and simplify this because we're supposed to know cosine of 30.
We
and
are
sine
supposed
of
to know
30, and
cosine of 30.
cosine of 30 is root 3 over 2, and you multiply it together, you get a 1,000 root 3.
Okay, and the sine of 30 is a half, and half of 2,000 is 1,000.
Okay, and then the cosine and sine of 45 is root 2 over 2, but the cosine of negative 45 is going to be positive. So we end up with, what is that, 450 root 2, and then sine's going to be negative root 2 over 2, so that's negative 450 times root 2. So how do we find the resultant vector of these two forces?
So the blue one is just the black one and the red one added together,
That's
right?
it. That's
We're
all
just
we gotta
adding
do.
those two things together.
So we add those together. All right.
You like how I show that?
That was amazing.
Okay. So we're going to have 1,000 square root 3 plus 450 root 2 and 1,000 minus 450 root 2.
All right, you could get a decimal approximation for that, but it actually asks us to find the magnitude of this vector.
Okay.
Well, that sounds like a lot of fun. How do we find the magnitude
Well, it's simply the square root.
of that first part squared?
Yep.
Woohoo. You notice we didn't round anything off, though?
Nope.
Because our final answer needs to be accurate to how many decimal places?
3.
Hey.
I believe if the board is cooperating, it all looks like that.
Okay, and the answer to that, if you typed it in, turns out to be 2,396.195.
Squish.
And that's a 5 if you can't see the edge of the board. Okay.
Alrighty.
Piece of cake?
Sounds good.
I think they're all a piece of cake. Maybe I'm hungry. I don't know. All right. What's
Unit vectors.
Unit vector. Well, a unit circle had a radius of what?
1.
So a unit vector is going to have a magnitude of?
1.
There we go.
I like these questions. Can I have another one?
So if you have something that has a length of 10, how do you
Uh-huh.
make it turn into a length of 1?
You divide by 10.
Sweet.
I like these questions. Can I have another?
All right. So if magnitude of vector m,
Uh-huh.
magnitude of the vector is m,
Okay.
and the component form is a comma b,
Then we divide by m.
we just divide the x and y
Components.
components by m,
Okay.
and we get the unit vector. We're literally just dividing it by the length.
Of the magnitude.
Perfect.
Okay.
So officially, if you look at this, you have vector u, which is a unit vector. That's what we're going to call it, unit vector.
Okay.
It's going to be the original vector divided by its magnitude.
Sounds good.
That makes it same direction, length of 1.
Perfect. We're just scaling it down.
All right, so let's try one.
All right.
What
so
do we need to find? if
We
we're
need to
gonna do
find the
this?
magnitude.
Find the magnitude. Magnitude's going to be,
The square root of 5 squared?
let's draw the correct notation. That is the magnitude of
Perfect.
vector, well, let's call this vector v. And there's the magnitude of vector v. It's going to be the square root of 5 squared plus 1 squared.
Square root of 26.
Okay.
So we have to take the components and divide by the square root of 26. So u then would be 5 over root 26, and you can leave it like that, and 1 over root 26. Ta-da.
Done. Happy. Moving on.
I like that.
Okay.
You're on a roll. Keep going.
Standard unit vectors.
Okay.
Standard unit vector means we're going to go 1 unit to the right and 1 unit up.
Okay.
So it's basically, we're taking our components and saying we're moving a unit on the x-axis and we're moving a unit on the y-axis.
Alrighty.
And for no other reason, we're going to call the unit to the right I,
I. Sounds
and the
good.
vector that goes the unit direction to the up, unit up.
Vertically?
Vertically, thank you. That's our math teacher. I know you use
what I'm
big
here
words.
for. I got
All
you.
right, so basically, I is going to go 1 way this way,
1 unit to the right. Okay.
and J is going to go 1 unit up.
Got it.
Okay? That's exciting. So what does this mean? This means if I have a vector in component form as c comma d,
Uh-huh.
I can write it as c times vector I plus d times vector j.
Okay. It's just another way
That
to
is
write
c
it.
to the right, d up,
Okay.
or down.
Sounds good.
So how does one do this? We want to find the component form of let u be the vector with initial point 2, -5, and terminal point -1, 3. So component form means I have to move it to the
Origin.
origin.
Okay,
So, how
so
do
the
I move
points
the
in-
initial point to -5 to the origin?
I'm gonna have to go left 2,
Left 2,
and I'm gonna have to go up 5.
up 5, and all we have
That's
to
gonna put
do
me back at the origin.
is the same thing to that. So move
Correct.
that left 2, and what do you get?
-3.
Put you on the spot, you gotta do
You
some math.
did, and 8,
There we go.
because 3 plus 5 is 8, all day long.
So, there's our component form of U. That wasn't hard, was it?
Right, and remember, we're moving the terminal point there, because the original point is at the origin.
Yep, this goes to 0, 0, basically.
Correct.
All right, linear combination of the 2 unit vectors. Well, this says I went 3 left and 8 up.
Correct. So that's going to be a -3 I, and an 8 up is in plus 8 J.
It really is that easy?
It really is.
All right. Okay, so last one.
Last one.
Last one. Find the unit vector. Okay, unit vector means the length is what?
Oh, what?
What is the length of a unit vector?
1.
1. So we need to find the magnitude of this vector, do we not?
Sure.
Sure. Okay. We have -1, -3j, but to find the magnitude, maybe it would be more helpful
In component form.
in
Thank you.
component form. So
That's
what
I
would
was
that
looking
be?
for. -1, comma -3.
Okay. So how do we find the magnitude of a component form vector?
It's simply the square root of the x component squared, so
Which is
-1
positive
squared,
1.
which is 1, plus the y component squared, and it's a square root of 10
Okay, so I find the unit vector then of this thing.
by dividing by the magnitude.
So I got
-1.
-1 over root 10.
Yep.
Whoa,
hope we're
there's a
almost done,
little
'cause
part
the
of this board
board's
that's just
losing it.
getting a little kind of loopy here.
Sounds like us.
We're a lot loopy. Okay, those are square root symbols in case they look like,
Not.
whatever. If we started with this thing in standard vector form,
Okay.
standard units, let's go ahead and rewrite it that way just for fun. This would be -10I minus 3 over the square root of 10j.
J. Yep.
And
And
those,
either of those answers would be correct. Yes?
yes,
Okay.
we good?
We're good. There's a little bit of notation at the end there. Make sure you read that and you're understanding all those different notations.
The math is just geometry.
It really is.
You just gotta learn all the vocabulary and figure out which geometry skill to use.
Yep.
All right,
We'll see you soon.
sounds good.